Okay, we will proceed to the next presentation by Anastasia Fragmentiti, the Department of Civil Engineering of the University of Patras in Greece, who will present a talk with the title Treatment of Primary and Secondary Effluent by Chlorococcum species.
Thank you. Good morning. My name is Andriana Aravantinou, and I'm a PhD student in the Department of Civil Engineering in the University of Patras. Today I will present you our work about treatment of primary and secondary effluent by an autotrophic microalgae, Chlorococcum species. First, in this presentation, we'll make an introduction about our subject for microalgae wastewater treatment and the selective microalgae species, which is Chlorococcum species. Then we'll proceed about to speak about the materials and methods which we used in our experiments, and then we will present some results about biomass production, nutrient removal, and lipid production of our microalgae cultivation. And finally, we make some conclusions. The aim of this study was to investigate the effect of primary and secondary treated wastewater on growth, nutrient removal, and lipid production of Chlorococcum species cultivated in a laboratory scale open pond. Specifically, the research target was to further improve the nutrient removal from wastewater and to investigate the potential production of renewable energy. Why this method is important? Natural system refers to sewage lagoons, sewage farms, stabilization ponds, and other algal reactors. Was first mentioned reported in the late 1800s in Berlin. It is important because the wastewater treatment with algae offers important advantages, such as low capital and operation cost, low energy requirements, contribution to reduction of carbon dioxide emission, but also use of algal biomass as fertilizer or fuel sources. And finally, the last decades, it's a great potential for algae to be used as biofuels. The selection of microalgae for potential biofuels production should take into consideration the high algal cell density, the high lipid content, but also their presence and survival in wastewater. But why to choose Chlorococcum species? Chlorococcum species are fresh water microalgae and soil green algae. The cell are spherical and the size are they have a high size 8 to 20 micrometer diameter, which is more effectively for harvesting. It's an autotrophic microalgae and with a high lipid content. It's a promising as one of sources for industrial production of astaxanthin, and it's a habitat in secondary effluent, as we found in previous experiments. And most importantly, it's high temperature tolerance up to 40 Celsius degree, which is important for our country. But before we talk about our experiment of this work, we should mention the primary research which was conducted before performing our experiments. First, we make an identification of suitable species and cultivation system. Then we make a determination of microalgae growth of 10 different species. We make a culture optimization, and we also make short-term experiments of nanoparticle and microalgae growth and their lipids. And then we study about different methods on microalgae because it's the highest cost in the plant for biofuel production. And at last, we make a scale-up in a pond, which is our experiment which we'll present today. Our experiments were conducting for Chlorococcum species in a laboratory open scale with a working volume of 30 liters. The conditions was stable, such as temperature, photo periods, and air supply. And the operation period was ranged from 7 to 46 days. The investigating parameters was changed, and it was the operation mode, such as batch, fill and draw, and continuous mode. The flow, also there was a change about the flow rate and hydraulic rotation time, the photosynthetic radiation intensity, and moreover, it was used primary and secondary sterilized treated wastewaters, which was supplied from the wastewater treatment plant of University of Patras. There were conducted two sets of experiments with Chlorococcum species. In the first set, we used primary treated wastewater, and the second set, we used secondary treated wastewater from an activated sludge treatment plant. In the first table, we see the first experimental set, which was combined from 6 phases with different modes at the operation days. The flow rate was the same, and the HRT was the same. But in phase 5 and phase 6, we see some of the investigating parameters, which was about the nutrients and the radiation intensity. In the second table, we see the second experimental set, which was combined from 4 phases. And we mostly, in this experimental set, we investigate different hydraulic rotation times. In this table, we see the measurements which we were conducting in our experiments. We measure biomass concentration with a gravimetric method, absorbance, chlorophyll, A, and turbidity. We also measure total nitrogen, nitrates concentration, total phosphorus, phosphates concentration, chemical oxygen demand, and soluble not particle organic carbon, pHD, and finally the lipid extraction, which was made from the dry biomass of microalgae. Here we see some results from forums. In the second figure, we can see the secondary treated wastewater experiment, which was combined from 4 phases. And we can see that we have a logarithmic phase here in batch conditions, and in phase 2. And we can see a stationary phase for phase 3 and phase 4. The highest biomass concentration was reported in primary treated wastewaters. The growth rate of microalgae for treating the secondary effluent was greater at even at low HRT compared to higher HRTs, hydraulic rotation times. Here we have our results about nitrates concentration. We can see from these results for the first experimental set that even in the inflow we don't have nitrates. They are present in the pond and in the effluent, and this is due to the presence of ammonium. In batch conditions, in all cases, expect the phase 1 of the first set, the removal was almost 100%. And we see that even at high concentrations of nitrates, we have a total removal which was up to 98%. In this phase, we don't have a removal of nitrates because we have a low concentration of phosphates. Phosphates and nitrates are essential nutrients for the growth of our biomass. And you see here the phosphates, which is very low. And we see that in the first experimental set, phosphates approach the 100%, especially in phase 6 with high radiation intensity, which give us the conclusion that there is a high photosynthetic reactions. Moreover, in this second experimental set, we can see that even at high concentrations we have in our wastewaters, we have a total removal of our phosphates. Finally, the lipid context of our dry biomass of microalgae Chlorococcum species, we can see in these two figures, we see that in batch modes, we have the highest lipid content. The highest lipid content is reported for the experiments which was used secondary treated wastewaters, which approached the 50% of our dry biomass of microalgae. We see that in the other modes, in the other phases, the lipid content was similar to the primary with the primary treated wastewater, which is close to 10%. And we should mention that usually in the wastewaters, the lipid content is lower than in cultivation with a media which is which have nutrients stables. In a previous study, we saw that in a media here, our Chlorococcum species approach 5% and 7% of our lipid content. To conclude, this research work combines wastewater with microalgae lipid productions. The biomass concentration of Chlorococcum species was increased with decrease the hydraulic rotation time. The efficiency of the pond to remove nitrates and the algal lipids content was affected by the nitrogen concentration in the effluents and the hydraulic rotation time. The lowest nitrogen removal and the algal lipid content of Chlorococcum species was observed at periods with high nutrient supply and short hydraulic rotation times. The highest lipid content of dry weight of microalgae was 15% and was observed when the culture was in low nutrients concentrations with secondary wastewater treated wastewater. In conclusion, the production of microalgae with high lipid content in wastewater is a new promising technology which requires further investigation. Our next steps is to scale up ponds with microalgae species with higher lipid content, such as Cnidarium surbensis, to investigate the long-term impact of nanoparticles on microalgae cultures which affect the lipid content, to investigate the cultivation of high lipid microalgae in outdoor ponds for wastewater treatment, and finally to investigate a low-cost harvesting method for microalgae biomass. We close with some pictures of our experiments, and thank you for your attention.
Okay, we do have some time for questions. Are there any questions?
I'd like to ask if you found any particular difference in the fatty acid composition of the individual fatty acid?
We didn't investigate the fatty acid. We started with lipid content to select the microalgae, and then we continue to investigate the fatty acids of our lipids.
You mentioned the possibility of using renewable energy. What about this? You mentioned in the slide
Yes.
the possibility of
Of
using renewable energy.
Yes. For biofuels, we cultivate microalgae to take biofuels, and this is our renewable energy.
Have you studied?
This we're trying to do, to see how we can minimize the cost for make a low-cost biofuel production. So we investigate which microalgae have high lipid content and have efficiently removal harvesting, because harvesting is the highest cost in these plants, and we investigate for this.
Will be the future research.
We hope. Yes.
Other questions? Okay, well, thank you.
Thank you very much.